Hello friends, my name is Narendra Singh and today I am here with a topic that is close to my heart as well as related with my experience, my past experience in the semiconductor industry, and the topic is SOC power and performance. This is a very deep topic which spans across the semiconductor CMOS technology and the SOC design and architecture, and also there is a huge role of software which makes use of efficient use of power. So all these aspects of SOC, or say a processor that is functioning, starting from the manufacturing to its design and architecture and software, all plays a role in power and performance. So let's discuss about it. So in our first chapter we are going to discuss the different components of power dissipation in the SOC. But before that, to make this presentation a bit wholesome and so that the new entrants in our semiconductor industry, fresh talent, they can understand and correlate the concept, we would like to discuss a bit about SOC, what generally SOCs look like today. So in general, SOCs will have multiple blocks. Those all blocks will be doing some dedicated task. Some of them will be interacting with each other, and there will be inputs and outputs from the external world. Okay, there can be processors, there can be one processor or multiple processor cores which are working synchronously, and many a time operating systems are very smart and they kind of do multi-thread their task and efficiently try to use all the cores running. That is also one aspect of saving power we will discuss in chapters to come. But yeah, let's discuss what an SOC looks like. So there can be processors, there can be memory controllers, there can be multimedia units. In multimedia there will be audio subsystem, there can be camera subsystem, there will be display outputs related blocks, display pipes, JPEG encoder decoder, camera along with camera subsystem, video encoder decoder, multiple hardware accelerators for multimedia basically. There can be, so this is a typical mobile SOC if we say, okay, so application processor, memory, multimedia, and wireless LAN connectivity, GPS, support for peripheral devices like eMMC card or your SIM card which gets connected, or sound related systems, or you can connect through multiple protocols like I2S is also there, microphone will be connected, right? And there will be some of the blocks for internal management itself, okay, and yeah, so basically, and there can be modem, right? There can be inbuilt modem in a mobile SOC particularly. So there are multiple blocks. So just to give you a picture that those are either, and mostly digital blocks, or sometimes analog or mixed signal IPs are also there. So SOCs are application specific. There can be mobile SOCs for say a mobile phone that you use, or there can be SOCs for PCs, laptops, right? So those processors are SOCs because they other than processor there is other there will be ecosystem, other blocks which acts as a system on chip. There will be SOCs for data center, there will be SOCs for graphics processors, GPUs, or network router, or a TV will have a SOC, or set-top box will have a SOC. All have dedicated applications. There will be dedicated SOC blocks, but more or less there will be similar way of operation. There will be some processor unit, there will be some memory, there will be some interconnect, there will be some interfaces. Okay, so that basic remains same. In this picture, we just want to give little bit more clarity on how complex one SoC can be, right? There are multiple cores available for processor. As a processor, multi-core processor is there, entire subsystem is there, DDR memory connectivity related controller will be there. There will be GPS related controllers are there, processing units are there, wireless LAN connectivity is there, audio subsystem is there, multimedia block, as I told you little bit, that will be there, and multiple other memories in the system, connectivity among them, because data needs to transfer to and fro for some of the processing, multiple peripherals, high speed and low speed, and some processors and cores for internal management. Okay, its role we will see in coming chapters. So this is a typical mobile SoC, just to depict the complexity and how much data processing happens and how that different tasks are assigned to different blocks in the SoCs, and they perform a particular function for you. Like in this case, a mobile SoC is doing all the jobs that you usually do in your smartphone. So now we come back to our topic, power and performance. So what is the driving factor why we want high performance, right? So like you want your PC to be very faster. What does it mean that you want higher frequency running cores? And why we want that? Because we want to run multiple applications all together. We do not want to feel any lag, and their applications are also have become intensive of consuming the CPU power as the CPU power is increasing. So our applications are also changing, and we want to run multiple applications at the same time. We want to feel a real life like feel that we do not want to experience any lag. So that all needs faster performance. Same way, if you are gaming and you want more real life like visualizations in your gaming, so that does mean that you are processing more frames per second, more and more frames for every visual, and in that ultimate, and that is also happening at a very fast speed, so that there is no lag. So all that requires a higher performance execution units which are processing those frames. Okay, and it's not only those execution units; it's the entire wholesome system for that performance, is from memory to that processing unit and the data transfer in between. So if there is a bottleneck anywhere in the performance, you will not achieve the end result. Okay, so what I want to depict here, that our life is depending more and more on digital processing today, everywhere, starting from financial to our PC, our data storage, and there was never a time before in which so much of pictures of humans were stored in these machines, which are ultimately memory and digital machines. So we are using more and more of these semiconductor devices, and we want higher performance out of it, and that's the motivation how we want higher, what drives for a higher performance, because we have more applications which are hungry of performance, and we want better experience. There will be some other applications which might require some computation or some sort of processing of some data in faster rates for a given applications. That also will be there, where there will be an exact requirement of particular performance. But what we discussed here, that in our real life or everyday life, how the performance of these SoCs can directly affect one of us, and how we can experience it. Now we talk about the power. So our SoCs or these chips consume power. We will see what are those components. But why are we even concerned about this power that is getting consumed? That's the topic I want to discuss in this slide. So very first point is that if you are using a handheld device like mobile phone or a laptop, which are battery operated devices, you want a better runtime of their battery, more battery runtime, right? You want your mobile phone to, once you fully charge, to operate for at least a day, and that depends on how efficiently we are using that battery energy, energy of battery, right? So that battery power needs to be efficiently utilized. So that is one motivation of saving power, or using power efficiently. Second case is there, suppose there is a grid power connected, there is no battery constraint, but still we want to save power, because end of the day our energy which we are consuming is, some of it is coming from renewable energy, some of it is coming from, say, atomic power or hydropower, but most of it is still, like at least in countries like India, comes from fossil power. And we save the energy, we save our fossil fuel, also we save our environment. So that's the motivation of saving the energy. Third motivation is that even if, suppose there is infinite energy available, there is a physical limit in form of thermal dissipation, because more the power SOC is dissipating, more the thermal heat is generated, and the high thermal dissipation will lead to higher temperatures, and that higher temperature can break your device, breakdown can happen. So that is also one of the motivation to keep the power dissipation low. So this was about the power, why we want to keep it low, and the performance we understood. We want higher performance almost everywhere, either it is your PC or it is your mobile, where you are running so many applications today. You are able to run so many applications because there is more processing power available, right? The camera through which I am shooting, right? How much resolution, the good picture you are seeing, because there is more processing power. That processing power is coming from the higher performance, maybe more CPUs, but also running at a higher performance, right? So that is the motivation. Okay. So now let's start talking about the components of power dissipation in the SOC. So as we were discussing that, in this picture I just want to depict that ultimately that SOC is dependent on one small piece of hardware that is called CMOS. Those SOCs are built of multiple blocks, those IPs, those can be analog or digital, or right, mixed signal IPs. Those are realized by combinational circuits, sequential circuits, memory elements, right, multiple FSMs. Those are realized by combinational circuit elements or sequential elements, mux, demux, encoder, decoders, multiple flops or latches, register files. Those ultimately are realized by gates. Gates are built by CMOS, and that CMOS consumes power. Okay, so let's focus on CMOS here. So this is a CMOS where there is, which is built of a PMOS and NMOS combination, right? So you must have studied all this in engineering, basic engineering. So what happens here, when the input changes and accordingly the output changes, during that is the switching, right? And during that switching, if that state is changing, in one state is there where PMOS is on and NMOS is off, so the capacitor charges. This capacitance is formed by interconnects, and some part of silicon also role is there, but ultimately there will be a combined effect of capacitance. It's that we are talking about. So there will be a charging phase where say output becomes 1 when PMOS is on, and this capacitor gets charged, and when state changes and PMOS turns off and NMOS turns on, it means this capacitor will discharge to ground and output becomes 0. So that switching causes power consumption, okay, power dissipation. So, and that power dissipation happens in this equation form, that is CV square and F. F is the frequency. The more switching is happening, the higher rate of dissipation, more power, okay, and it is directly proportional to C and V square. So We will see the techniques in which we can minimize the V, that is the voltage, and voltage of the CMOS, and the overall effective C, the capacitance, how we can reduce, we will see. But this is the basic of switching power, one of the components of power dissipation inside SOC. There is one component of power dissipation that is called short circuit power, and before that I just wanted to illustrate that how PMOS and NMOS are fabricated in the silicon. Okay, and ultimately there will be CMOS where there will be a N well inside which a PMOS is constructed, and then the P substrate there will be NMOS, and this PMOS and NMOS together form a CMOS, which is the basic building block of all the gates which relies over digital circuits. So in this CMOS, there is one component that is called short circuit power, because when the transition happens from 0 to 1 or 1 to 0, there is small fraction of time in which when the PMOS is turning on and NMOS is turning off, or vice versa, there is a small fraction of time when both of them are on, and there is a little peak of the current for a small transient of time, that is called short circuit current. Okay, and this power which is getting dissipated is called short circuit power. Okay, this is the second component. There is one more which is more prominent component. This is called static power. Okay, static because while the switching is not happening, even then this power is getting consumed. Okay, and that is called leakage currents. So these leakage current can be, there are multiple components. We will not go into the physics of these currents because that is not the agenda. I just wanted to understand here that there are different current leakage currents components and how we are going to control them later. Okay, so there are some components. One is like reverse bias PN junction leakage, that you must have read in your electronics courses. There is sub-threshold leakage, which is one of the major contributor actually, and there are some other components which is called gate leakage tunneling current, and there is another gate leakage component due to hot carrier injection, right, and GIDL, that is called gate induced drain leakage. So these are different components of leakage current which form our leakage power in a CMOS. And for a CMOS there is a threshold voltage, right? You know threshold voltage when the gate source to gate voltage is applied, like in case of PMOS, if it is applied more than that, then the channel conducts, right? And if it is lesser than threshold voltage, and this channel do not conduct. Below gate the channel formation does not happen. So that threshold voltage has a direct dependence on the leakage power. Temperature also has a direct dependence on the leakage power, and this threshold voltage in turn is depending upon the construct of the CMOS as well. So what is the length of the gate, and what is the depth of these drain and source, how deep those are, and it will also depend upon the thickness of the gate dielectric, also depend upon the doping concentration. All those factors will somehow in result affect the leakage currents. So more prominent factors are temperature and the VTH. If we can control the VTH, we can control the leakage current, and primarily that is the sub-threshold current. Okay. So this fact I am stating just because we will be using this fact in coming slides for when we will work on how to reduce the leakage power. So as I was mentioning, this equation you must have studied already, that how the reverse biased current depends on the temperature, and it's exponentially increases with the temperature actually. And then there is this more important prominent component of the leakage, that is sub-threshold leakage, and it affects on the channel length, gate width, drain voltage, and drain induced barrier lowering, the drain which affects the actually gate. So the voltage applied at drain, it starts affecting there, and as we are reducing the gate length more and more, that this effect is becoming more prominent actually. So that is one of the factors that will decide how much leakage is there. And there is some of the techniques which we will study, that how we control this leakage. One of them is body bias. So the body bias, the substrate, if how we bias it, and that can actually reduce the that will basically affect the threshold voltage, and that in effect will change the leakage current. And obviously temperature effect is there, exponentially rise happens in the leakage currents with temperature. All right, so in this chapter we wanted to discuss this much. We studied what SOCs look like today, why we want higher performance, what is the intent behind keeping the power dissipation low, what are the different components of power being dissipated inside SOC. So okay, so in our next chapter we are gonna discuss the dynamic or switching power, how we are gonna reduce. So we take a little pause here and then we will resume.